Welcome back to the Deep Dive. Today, we're diving deep, really deep, into some pretty tricky parts of distributed systems, specifically database transactions.
Yeah, we're looking beyond the basics today.
Right. We're tackling concurrency and those race conditions that aren't, immediately obvious. Maybe you've bumped into things like dirty writes or lost updates. We're going past those.
Absolutely. Those are fundamental, sure. But when you get to senior level stuff, interviews, complex systems, you really need to grasp the subtler failure modes.
And that's what we're focusing on, right, skew, and phantoms.
Exactly. These can cause some really nasty bugs, hard to track down in production systems, and definitely topics that come up in system design interviews. They test your depths of understanding.
Okay, so that's our mission for this deep dive. Let's unpack right, skew, and phantoms. What are they, really? How are they different? Why do common tools, like certain isolation levels, miss them?
And critically, how do you prevent them? What are the trade-offs?
Yeah, and how do you talk about all this confidently, say, in an interview? We want you to walk away with that solid, actionable knowledge.
All right, let's start with the right skew anomaly. A really classic example, you often hear about this one, involves managing on-call staff, like doctors at a hospital.
Okay.
Imagine Alice and Bob are the only two doctors on call for a particular shift. And there's a hard rule. You must have at least one doctor on call at all times.
Got it. So the constraint is currently on call greater than or equal to 1. Minimum 1 person.
Right. Now, let's say concurrently, Alice decides she needs to go off call. And at pretty much the same time, Bob also decides he needs to go off call.
Yep. Concurrent requests. What happens in the database? They're probably using something like Snapshot isolation level.
Very likely. Many systems default to levels like snapshot isolation or repeatable reads, often implemented using MVCC, that's multi-version concurrency control. It gives each transaction its own consistent snapshot of the database when it starts.
So no immediate locking, usually. Each sees the world as it was when they began.
Pretty much. So Alice's transaction starts. It runs a query, maybe select count star from doctors, where on call equals true and dshift ID equals 1234.
And it sees 2 doctors, right? Alice and Bob.
Yep. And Bob's transaction, starting around the same time, runs the same query in its snapshot. It also sees 2 doctors.
Okay, so both of their application logics check the rule. Is 2 greater than or equal to 2? Because you need 1 less if 1 leaves.
Correct. And the answer is yes. So both transactions think it's safe to proceed.
Ah, I see where this is going.
Alice's transaction goes ahead and updates her record. I update doctor set on call equals false, where name equals Alice and shift ID equals 1234.
And Bob's transaction updates his record. You update doctor set on call equals false, where name equals Bob and shift ID equals 1234.
Right. Now, under snapshot isolation level, what does the database see?
Well, they updated different rows. Alice updated Alice's row, Bob updated Bob's. There's no direct right conflict on the same piece of data.
Exactly. So from the database's perspective, using snapshot isolation, these look like independent, valid updates both transactions are allowed to commit.
And the result.
Yeah.
Uh-oh. Both Alice and Bob are now on call equals false. 0 doctors on call.
And you've violated your critical business rule. That's the right skew anomaly.
Okay, so let me try to define it then. Right skew it's a race condition where you have 2 transactions. They read some overlapping data, like the set of on-call doctors. They use that read to make a decision.
Yep.
And then they write to different objects or rows. But those writes, when combined, violate some kind of rule or constraint that was based on the state they initially read.
That's a perfect summary. The key is that the conflict isn't on the right target itself, like in a lost update where both try to update the exact same field. It's that the right invalidates the premise or the precondition that the other transaction checked. It's almost like a generalization of lost updates in a way. Lost updates are when read set and write set are the same. Right skew is when read sets overlap, but write sets are disjoint, yet still conflict logically.
And why does snapshot isolation level struggle with this? It seems like it should catch concurrency issues.
Well, snapshot isolation level is great at providing a consistent view at the start and preventing conflicts if transactions try to write to the exact same rows. But it doesn't really track the relationship between the data read and the data written across different objects for complex application level rules.
So it doesn't see that Bob's write just broke the rule Alice checked based on her earlier read.
Not inherently, no. Especially when the check involves like an aggregate count star or a scan over multiple rows that Bob isn't directly updating himself. His write doesn't conflict with Alice's read in the way snapshot isolation typically detects conflicts. Her read was consistent then, but the world changed in a way that invalidated her decision.
Okay. And you mentioned this is common in interviews, like a candidate just saying, oh, I'll select the count, check it, then update.
Huge red flag. Assuming snapshot isolation level just handles everything is a common mistake. You find snapshot isolation or repeatable read in PostgreSQL, MySQL, InnoDB, SQL Server. It's widespread. But it does not automatically prevent the right skew anomaly. Even older Oracle versions claiming serializable sometimes needed specific hints or techniques.
So if snapshot isolation level isn't enough, and maybe going full serializable isolation level is too slow, what do we do? How do we prevent this doctor scenario?
Well, in this specific scenario, notice that the rows being updated, Alice's and Bob's, were part of the set of rows read initially to check the count.
Ah, okay. The select count star, where on-call equals true, read both their rows.
Exactly. When that happens, when the decision depends on rows you might later modify, explicit locking using the select for update statement is often the way to go.
Okay, walk me through that. The pattern is check, decide, act. How does select for update statement change it?
Instead of just selecting, you select and lock immediately. So Alice starts her transaction. Her first step is select star from doctors, where on-call equals true and do-shift ID equals tool34 for update clause.
Got it. For update clause at the end, what does that do?
It acquires exclusive write locks on all the rows returned by that select query. In this case, it locks Alice's row and Bob's row.
Okay. So if Alice gets those locks first,
then if Bob's transaction concurrently tries to run the same select for update statement, it hits those locks and has to wait. It blocks.
it can't even read the count until Alice is done.
Right, until Alice's transaction commits or rolls back and releases the locks. So Alice proceeds. She checks the count, still 2 in her view, decides to go off call, updates her row, and commits.
Now the locks are released.
Yeah.
Bob's transaction wakes up.
Exactly. It acquires the locks, now runs its read. But Alice's change is committed, so Bob's select for update statement now only finds one doctor on call himself.
Ah, so his check is 1 greater than or equal to 2 fails.
Correct. His application logic prevents him from going off call. The lock forced the operations to effectively happen sequentially for that critical check and update part, preventing the anomaly.
Okay, that makes sense for the doctor case because the read set included the rows being updated.
Yeah.
But what if the check is about something not being there? Like checking if a resource is free before claiming it. The read might return 0 rows.
Yes. You've just hit on the problem of phantoms. That's the next piece of the puzzle.
Phantoms. Okay, what are they?
A phantom happens when one transaction executes a write, usually an insert or delete, that changes the set of rows that would match a search condition used by another concurrent transaction.
So like transaction A checks, are there any meetings in this room at noon? It finds none. Transaction B then inserts a meeting for noon. If transaction A checks again, it suddenly sees a row that wasn't there before a phantom.
Exactly. Or a row disappears. The set of rows matching your query condition changes mid-transaction due to someone else's committed write.
And how does this relate to write skew?
Phantoms enable a really difficult type of write skew, especially when your logic relies on the absence of something. Your select looks for conflicts and finds none. Because the conflicting row doesn't exist yet, it's a phantom. Based on finding nothing, you proceed to insert something, but someone else does the same thing concurrently.
And the select for update statement trick doesn't work.
How can it? If your initial select key, where condition returns 0 rows, what is there to lock with for update clause? You can't lock rows that don't exist.
Right, you can't lock the phantom.
Precisely. This brings us to those other classic examples.
Like meeting room booking.
The classic. Check if room 123 is free from noon to 1 p.m. If yes, insert my booking. The check looks for existing bookings that overlap that time slot.
So SQL might look something like start transaction, select count star from bookings where room ID equals 123 ND end time greater than January 1st, 2015 at 12:00 ND start time less than January 1st, 2015 at 13:00.
Exactly. Check for overlaps.
If that count is 0.
Then you insert into bookings room ID, comma, start time, comma, end time, comma, user ID values 123, comma, January 1st, 2015, 12:00, comma, January 1st, 2015, 13:00, comma, 666, and commit.
Okay. Now, 2 people try this concurrently for the same room, same time slot.
Both run the select count star. Both see 0 results in the respective snapshots because neither booking has been inserted and committed yet.
Both think the room is free. Both proceed to insert.
And boom, double booking. 2 rows inserted for the same resource at the same time, violating the implicit constraint that a room can only have 1 booking per slot.
And select for update statement on that initial count query doesn't help because it returns 0 rows, nothing was locked.
Correct. The phantom was the absence of a conflicting booking. The insert made the phantom real, but too late. This is prime interview question material. Design a booking system, prevent double booking. Just doing select then insert is the naive approach that fails.
I know PostgreSQL has, like, range types that can help here sometimes.
It does, yes. PostgreSQL has specific features like range types and exclusion constraints that can elegantly solve this particular overlapping time problem. But that's database specific. Not all databases have that.
Okay, what about the multiplayer game example, moving pieces?
Right. Let's say you want to prevent 2 pieces from moving to the same square, say C4. We know we can use select for update statement on a specific piece's row to prevent lost updates on that piece, like if 2 players try to update its score simultaneously. Maybe select star from figures where name equals robot and game ID equals 222 for update clause.
Okay, that locks the robot figures row.
But that doesn't help prevent 2 different figures from moving to the same destination square C4. The check is different now. It's something like select count star from figures where position equals C4 and D game ID equals 222.
Checking if C4 is occupied.
Yes. If player 1 wants to move figure A to C4 and player 2 wants to move figure B to C4 concurrently, both run the check. Both see C4 is empty, count is 0. Both proceed to update their respective figures' row to set position equals C4.
Another double occupancy problem, caused by a phantom. The phantom is the empty C4 square. Locking figure A doesn't stop figure B.
Precisely.
Claiming a unique username seems similar. Check if coolcoder123 exists. If not, insert it.
Same pattern. Select user where username equals coolcoder123. Expect 0 rows. If 0, insert new user. 2 concurrent requests. Both see 0, both try to insert. Phantom is the absence of coolcoder123.
But there's a better way here, right?
Absolutely. Databases are really good at uniqueness checks. You just put a unique constraint on the username column in the user's table.
Okay.
The database itself will enforce this. When the second transaction tries to insert the duplicate username, the database detects the violation of the unique constraint and automatically aborts that second transaction. Simple, efficient, correct. Use constraints when they fit the rule.
That's much cleaner. Constraints are great for single-column rules like uniqueness. Okay, one more. Double spending, like spending loyalty points.
Very common. You need to ensure a user doesn't spend more points than they have. The check is typically select current balance from accounts where user equals X, or maybe select some points from transaction log where user did X.
Check if balance greater than or equal to amount to spend.
Right. If it is, you then record the spending, maybe by inserting a new row into a transaction log table with a negative point value. Insert into transaction log, user points, values, X, amount to spend.
Okay, so user have 100 points. Transaction A wants to spend 60. Transaction B also wants to spend 60 concurrently.
Both read the balance. Let's say they both calculate it as 100 based on existing transactions. Both see 100 greater than or equal to 60.
Both think they can proceed.
Both insert their netx 60-point transaction record.
Resulting balance is now 160. 60 all equals 20. Oops, constraint balance equals 0 violated.
Yep. Again, the check was on an aggregate, the sum or balance, and the right was an insert of a new row changing that aggregate. It's a phantom effect on the sum. Select for update statement on existing transaction rows doesn't really apply cleanly to locking against a new row being inserted.
Okay, so we've seen snapshot isolation level allows right skew and phantoms. Select for update statement helps sometimes, but struggles with phantoms, where we check for absence. What's the ultimate weapon? The one that stops all of this?
That would be the serializable isolation level.
Serializable, highest level.
Right. It provides the strongest guarantee. It ensures that the result of running concurrent transactions is identical to some serial one after the other execution. The database effectively detects any interaction that could violate this serial equivalence, including right skew and phantoms, and typically aborts one of the conflicting transactions.
Wow, okay, so it just handles it. Why don't we just use serializable isolation level all the time then?
Performance, that's the big trade-off. Serializable isolation level is almost always the slowest, least scalable level.
Why? What does it do? More locking.
It often involves more aggressive locking strategies or complex dependency tracking and conflict detection mechanisms. This can lead to significantly reduced throughput, higher latency, and more transaction aborts, especially when there's a lot of contention or in distributed systems.
So gold standard for correctness, but potentially a killer for performance. Another key interview trade-off discussion point.
Absolutely critical. Knowing when the correctness guarantee of serializable is worth the performance cost is a mark of experience. You need to weigh the risk and impact of an anomaly against the performance needs of the application.
Okay, but what if serializable is just too slow for our system and select for update statement doesn't work because we have that phantom problem like the booking system, checking for the absence of a booking? Is there another way?
There is a technique, sometimes seen as a bit of a workaround, called materializing conflicts.
Materializing. Making the conflict real, tangible.
Kind of, yeah. The core problem with phantoms in the booking system was the check select count star returned 0 rows, so there was nothing to lock with the update clause. Materializing conflicts means you deliberately change your database schema to create concrete rows that represent the abstract resource or constraint you're trying to protect.
Okay. How would that work for the booking system?
Instead of just having your bookings table, you might create an additional table. Let's call it room times lot locks. Each row in this table could represent a specific room for a specific discrete time block, maybe every 15-minute interval. So you'd have rows like room at 123, slot start 2015, 01101, 12.00, room at 123, slot start 2015, 0101, 001, 12.15, and so on. You'd pre-populate this table for all bookable slots.
Okay, so you have actual rows for every possible slot. Then what?
Now, when a transaction wants to book room 123 from noon to 1 p.m., before it even checks the bookings table, it first tries to acquire locks on the relevant rows in the room time slots locks table. It would do a select for update statement on the rows for room 123 at 12.00, 12.15, 12.30, and 12.445.
Ah, so now there are concrete rows to lock.
Exactly. By locking these placeholder slot lock rows, you serialize access to that specific time slot. If transaction A gets the locks, transaction B has to wait. Once transaction A has the locks, it can then safely check the actual bookings table and insert its booking, knowing no one else can interfere with that time slot until it commits and releases the slot locks.
That's clever. You turned the phantom, the available time slot, into a set of actual rows you can lock.
It solves the problem, yes. But look at the trade-off.
No flexity.
Definitely. Your schema now includes tables and rows whose main job is just concurrency control, not storing primary business data. You have to manage these lock rows, pre-populate them, maybe clean them up. It can make the data model feel a bit artificial.
Yeah, it feels like a workaround.
It often is. It's usually considered when serializable isolation level is deemed too slow, and select for update statement on the actual data doesn't work because of phantoms. Kind of a last resort for strong consistency in those cases.
Okay, so besides constraints, serializable, explicit locking, and materializing conflicts, any other related techniques people might mention?
Well, within the database, sometimes people try using triggers or maybe materialized views to enforce complex rules, but that gets really complicated and database specific quickly. Not usually the first choice.
More broadly.
Yeah.
Like system architecture level.
Yeah, especially in distributed systems where maybe you don't have a single database providing strong ACD guarantees across everything. You start seeing patterns like the Saga pattern, which orchestrates a series of local transactions with compensating actions if something fails, or event sourcing, where recording events in an append-only log can sidestep some update conflicts. CQRS command query responsibility segregation separates read and write paths, which can reduce contention, or sometimes things like two-phase reservation systems, where you reserve a resource first, then confirm it later.
Right, those are more about handling things when maybe traditional transactions aren't feasible or scalable.
Exactly. And scalability is a huge dimension here. Simple locking with select for update statement can become a major performance bottleneck if many transactions need the same lock.
And serializable isolation level.
Yeah.
You said it gets much harder in distributed systems.
Massively harder. Implementing true serializability across multiple database shards or geographically separate nodes is extremely challenging. You run right into the trade-offs described by the CAP theorem: consistency, availability, partition tolerance. Getting strong consistency often means potentially sacrificing availability during network partitions, for instance. Understanding how these low-level transaction issues impact high-level system scalability and availability is crucial for senior engineers.
Okay, that's a lot to digest. Let's do a quick recap before we try a mini interview scenario.
Sounds good.
So first, write Skew. It's real, it's subtle. Concurrent transactions read overlapping data, make decisions, write to different places, but together break a rule, not the same as a lost update.
Check. And crucially, snapshot isolation level, while common and useful, does not automatically prevent write skew or phantom-based write skew in read-write scenarios.
Phantoms. When a write by one transaction makes rows appear or disappear for another transaction's query. Makes locking based on absence, select returns 0 rows, using select for update statement really hard.
Right. The main prevention tools we discussed: serializable isolation level, strongest guarantee, but often highest performance cost.
Explicit locking with select for update statement good when you can lock the rows involved in the check before acting, but limited by phantoms.
Materializing conflicts, a technique to create lockable rows for phantoms, but adds complexity.
And database constraints like unique constraints, fantastic when the rule fits. Let the database handle it.
And always be suspicious of that check, decide, act pattern in code or designs. Ask yourself, what happens if two transactions do this at the same time?
Perfect. Ready for a quick interview simulation?
Let's do it. Hit me.
Okay, imagine you're designing an inventory system. Basic stuff. Users buy items. You absolutely must prevent overselling transactions. You can't sell more items than you have in stock. So walk me through the potential race condition if two users try to buy the very last item concurrently. What's the problem and how would you solve it? Discuss isolation levels, trade-offs.
Okay, good one. The core invariant is quantity sold, initial stock, or maybe tracking current stock equals 0. The typical flow is check current stock. If stock quantity needed, then decrease stock and record the sale.
Right. The check decide act.
Exactly. So the race condition, stock is 1, user A wants 1, user B wants 1. They both start their transaction maybe under snapshot isolation level.
Both select stock from products where producted equals widgets. Both read 1.
Both check, is 1 greater than or equal to 1? Yes. Both decide to proceed. User A calculates new stock 1 equals 0. User B also calculates new stock 1 equals 0.
Both attempt to update products, set stock equals 0, where producted equals widgets.
Under snapshot isolation, if they update the same row, usually one might wait or one might fail depending on the specific implementation. Like first committer wins, second one might get a serialization error. But the logic based on the initial read was flawed. Both thought they could take the last item. If both somehow commit successfully resulting in stock 0 but 2 sales recorded, you've oversold. This is fundamentally a write skew. The concurrent writes, based on the initial shared read, violate the inventory constraint.
Okay, how do you prevent it reliably?
The absolute safest way is serializable isolation level for the entire check, stock, and purchase transaction. The database guarantees the transactions behave as if they happened one after another. So one user gets the item, stock goes to 0. The second user's transaction, when it effectively runs, sees stock is 0 and fails the check. Overselling prevented.
But the trade-off?
Performance again.
Yeah.
Especially for popular items, making all purchases serializable could create a bottleneck. Lots of waiting or transaction aborts and retries, leading to slower checkouts.
So what's a more common practical alternative if serializable is too slow?
For this specific decrement a counter pattern, explicit locking is very effective and often preferred. Use select for update statement.
How exactly?
The transaction starts, and the very first thing it does related to stock is select stock from products where producted equals widgets for update clause.
Lock the row before checking the value.
Precisely. This acquires an exclusive lock on the widget's inventory row. If user A gets the lock, user B's transaction trying to do the same, select for update statement has to wait. User A checks the stock, reads 1, proceeds, updates stock to 0, commits, releases the lock.
Then user B gets the lock.
User B acquires the lock, now reads the stock, sees E0, the check 0 is 1, fails. User B cannot purchase, correctness maintained, overselling prevented.
And this is usually less overhead than full serializable isolation.
Generally, yes. Locking just the specific rows you need is often much more performant than the broader guarantees and mechanisms of serializable isolation level, assuming contention on that single row isn't pathologically high.
What about just putting a database check constraint, like check, stock 0 on the table?
That constraint is good practice anyway as a safety net. But it doesn't prevent the race condition itself under weaker isolation levels, like snapshot isolation. Both transactions could read 1, calculate 0, and attempt to write 0. The final state, stock, might satisfy the constraint, but you still process 2 sales when only 1 item was available. The lock with select for update statement prevents the race condition during the transaction, ensuring the check and update are atomic relative to other attempts on the same item.
Excellent. Yeah, breaking down the problem, identifying the check then act, comparing serializable with explicit locking, and hitting those trade-offs that really shows solid thinking for an interview context.
Exactly. It's about understanding the tools and choosing the right one for the specific problem and constraints.
Phew. Okay. That was definitely a deep dive. Understanding right skew, phantoms, and how isolation levels and locking interact. It's not just theory. It's fundamental to building systems that actually work correctly under load. Debugging weird issues like double bookings or negative balances often leads right back here.
It really does. And like we touched on, start thinking about the next level. How do these problems change when your data is distributed, sharded across multiple databases? How do you coordinate locks or ensure serializability across different machines, different networks? That opens up a whole new layer of challenges and architectural pattern.
Definitely food for thought and something to keep exploring. Well, thanks everyone for joining us on this deep dive into right skew and phantoms. We hope this helps you build more robust systems and ace those interviews.
If you found this valuable, definitely give us a like, subscribe for more, and drop a comment below. Share your own tricky concurrency stories or questions. We all learn from each other's experiences.
Absolutely. We'll see you on the next deep dive.